So looks like in class you guys talked about non-homogeneous systems today, where basically the equilibrium isn't just the origin right off the bat. We should talk about that. Kind of want to spend a little bit more time talking about the trace determinant stuff we'd end the class with last time. I don't know if that's super important. Hmm. Let's do a couple examples of trace determinant stuff, and then we'll move on and talk about the other thing. So let's look at a few examples. So we want to classify the stability of the following systems where so basically if someone gives you a 2 by 2 matrix, you're supposed to be like, okay, that's a system where the first row is like dx dt equals whatever times x plus whatever times y. The second row is dy dt equals whatever times x plus whatever times y. So for example, when I give you the matrix A equal, if you say -1, -1, 5, -3, we know that means we're talking about the system dx dt equal to -x plus y, dy dt equal to 5x minus 3y. We don't need to write that down. We're just all on the same page. Or you can use x1 and x2, right? Either way, x and y, x1 and x2, same difference. So we want to classify the stability of the following systems, or I should say the classified stability of the equilibria of the following systems, sorry, of the equilibria, it's just one equilibrium of the following systems. For this system, our equilibrium is still 0, 0, right? It's just a regular 2 by 2 matrix. There's nothing special going on here. And we're going to do it the other way. So we're going to find the trace and the determinant. So the trace, in this case, is going to be, we use tau, is equal to -1 plus -3, which is -4. The determinant, which we call delta, is going to be -1 times -3 minus -1 times 5, which is going to be 3 plus 5, which is 8. All right, so here's how I usually break it down. If the determinant's negative, you're done. You have a saddle. It's kind of like how when we were classifying extrema of functions of two variables, and if your quantity d, which is equal to fxx times fyy minus fxy squared, if d was negative, you got a saddle. Same kind of deal. So if your determinant's negative, saddle. I'll remind you of the picture we drew last time at the very end, where we talked about how if you have the trace on the x-axis and the determinant on the y-axis, down here is saddle land. What I like to call it, saddle land, where the determinant's negative. Up here above the x-axis, you have either spirals or nodes. And the determining or the cutoff is this parabola. I never remember the equation of this parabola. It's silly, but I should know it. But really, what I'm thinking about that parabola is it's the defining line between having imaginary versus real eigenvalues. So I know it's where the inside part of the square root is either positive or negative. So I think about it, I know that when I'm finding like the oh my gosh, the quadratic formula and finding the inside of the square root, which is called the discriminant, that's where I'm saying the inside, which is tau squared minus 4 times delta, that needs to be positive for having a real one, negative for having a imaginary. So if it's greater than 0, it's going to be real. If it's less than 0, it's going to be imaginary. So this here, if we think about delta being y and tau being x, if we solve this for delta, we essentially have tau squared equal to 4 delta, or tau squared divided by 4 equal to delta. I never remember what I really like. I'm like, okay, let me figure it out. So this parabola is delta equal to tau squared divided by 4. And then if you're above it, we have spirals in here, spirals up in here, and nodes over here. So spirals, nodes. stable on the left, unstable on the right. So stable if tau is negative, right? If your real part is negative, if your eigenvalues are negative, we get stability. Unstable if tau is positive. So the question is, do we have a spiral or a node? Because tau, so determinant positive, not a saddle. Tau negative, stable. And then are we above this line or below this line? So the question is your determinant bigger than tau squared over 4? Let's see. Our determinant is 8. Is 8 bigger than negative 4 squared over 4? It's not. Or it is. Sorry, it is. So yeah, it is. Apologies. It definitely is bigger. So that's going to be that. So we're up here in the spiral land, so we have a stable spiral. Okay, I want to point out, I don't think this is the best way to do it. But some people like to do it this way. I think it's much, much easier just to find the eigenvalues. Right? I feel like this is introducing a whole nother level of complexity. But here's what I'll say about finding the eigenvalues. I do like finding the eigenvalues in the following way. So instead of doing what we've normally done, I do kind of like the fact that when you're finding the eigenvalues here, you're really just solving lambda squared. I always forget what it is. Minus the trace times lambda plus the determinant equal to 0. That is always what you're getting. So yeah, I don't know how I feel about that really, to be honest. Like you could do this. So the real truth here is you could do this any one of 3 ways, right? You could just find the eigenvalues the normal way, you can find the eigenvalues using this equation and the quadratic formula, or you could not even bother finding the eigenvalues and say, what have I got based on what's going on here? I wish I could give you better direction as far as like what you should do. The real answer is you should do what you think is easiest until someone says do it a specific way. So let's do one more. Let's say our matrix was A equal to -2, 3, 1, -4. And we'll do this in 2 ways, just so you can see both ways. So we'll do it the normal way. The typical way where the determinant of A minus lambda I is equal to -2 minus lambda times -4 minus lambda time minus 1 times 3, which is going to give us lambda squared plus 4 lambda plus 2 lambda is plus 6 lambda plus 8 minus 3 is plus 5. The nice thing about doing it this way is sometimes things will factor and you have to use the quadratic formula. So here, this does factor as lambda plus 5 times lambda plus 1. So we get lambda equal to -5 and -1. And we know if they're both negative, we have a stable node. So we know we have a stable node. Or to look at it the other way, I can say my trace is -2 plus -4, which is -6. And my determinant should be -3. Let's check. Sorry. Looking at my notes here. Okay, yeah. That's a 3 there, right? Yeah. My determinant is not, sorry, I made a mistake. My determinant is 5. Apologies. I was looking at this over here to see what my determinant was, but I should have been looking right here. So just as a reminder, that number there is the opposite of the trace. That number there is your determinant. And our determinant is 5. It's -2 times -4 minus 3 times 1, which is 8 minus 3, which is 5. So again, determinant being positive, not a saddle. Trace being negative, stable. But then we're not sure if it's a stable node or a stable spiral. So we have to figure out if we're above that parabola in spiral land or below that parabola in node land. So the question now is the determinant bigger than tau squared divided by 4? I always ask, is it bigger than, just because that's the way it makes sense for me to ask it. I don't really know. So this question really is asking, is it a spiral? Because if you're above the parabola, we're in spiral land. If you're below the parabola, but still above the x-axis, you're in node land. So let's see. Is our determinant 5 bigger than -6 squared over 4, which is equal to 36 over 4, which is 9? Obviously not. No. So we're not in spiral. It's not a spiral. It's a node. We have a node. Okay, I just thought of something that I think might be kind of clever, but it's probably not that clever. If you ask the question this way, is delta bigger than tau squared over 4? And the answer is no, you have a node. It could be worse. If the answer is yes, you have a spiral, which doesn't do anything fun. But okay, I kind of like that. I'm not gonna lie. So we have a node. So we have a stable node. I will point out if you're doing it this way, you should always, you should always look at the determinant first, because if the determinant's negative, you're done. You have a saddle. Doesn't matter what the trace is, right? If your determinant is negative, whether your trace is positive or negative or positive, you're still getting a saddle. So end of story. If determinant is negative, saddle all day long. Okay, I feel like that's enough of that. I will again point out you can do it whichever way you like. Yeah. Which thing? This picture here? Tau. So these are just Greek letters. So capital delta, you're probably familiar with. Lowercase tau is just a Greek letter. It's spelled T-A-U. So yeah, let me write this down here. Sorry, one second. Tau is just T-A-U. Tau.
And that's going to be the same?
No. So tau is the trace. So the trace. So sure, fine. Leave that on the floor. So in general, for a matrix A, B, C, D, or for any square matrix, actually, although we only deal with 2 by 2s, the trace, which we're calling tau, is just the sum of the diagonals. And the determinant, which you already know, which we're calling capital delta, is A times D minus B times C. That's what we're using here. But then I also point out, just so you can see it, if you're trying to find the eigenvalues in the normal way, check it out. The determinant of A minus lambda I is just going to be the determinant of A minus lambda, B, C, D minus lambda. And if you multiply this out, you get A minus lambda times D minus lambda minus B times C. And if you simplify this, check out what you get. You get lambda squared minus D lambda minus A lambda. So minus A lambda minus D lambda plus A times D minus B times C. And if I rewrite this just a little bit, this is lambda squared minus A plus D times lambda plus AD minus BC. Oh, look, it's exactly lambda squared minus the trace times lambda plus the determinant. Always, every time. It's kind of neat. Another fun fact, whatever your eigenvalues are, so even whether they're imaginary or real, it is always true that your eigenvalues multiply to the determinant and add up to the trace. So if your determinant's negative, it means your eigenvalues had to be opposite signs. Meaning you have one positive eigenvalue, one negative eigenvalue, which means you have a saddle. On the other hand, if your eigenvalues are both positive or both negative, then you have a positive determinant. And if they're both positive, your trace is positive, so you're unstable. And if they're both negative, your trace is negative, and we see that they're stable. For imaginary, same thing is still true, right? If my eigenvalues were, say, just say lambda equal to, 3 plus or minus 2i, those eigenvalues multiply to a positive number, right? 3 plus 2i times 3 minus 2i is going to be 3 squared. The middle terms cancel. You get minus 4i squared, which means you're adding 4. You get 9 plus 4, which is 13. And if you add them together, 3 plus 2i plus 3 minus 2i, the imaginary parts cancel out and you get 6. So if your eigenvalues are complex with a positive real part, you're going to still get a positive trace and a positive determinant. On the other hand, if that was a -3 instead of a +3, you'd still get a positive determinant here, but now your trace would be a -6. So everything corresponds as it should. It's kind of neat though that this is actually totally true. I think that's kind of one of the neatest things about it. And actually, if you ever take like, I don't think any of you have to ever take linear algebra, but if you ever took linear algebra, this fact actually is true for larger matrices as well. If you have a 3x3 matrix, the trace is the sum of all 3 of your eigenvalues, and the determinant is the product of all 3 of your eigenvalues. It's kind of cool. It's actually super useful if you take linear algebra. Anyway, let's stop talking about that and talk about some non-homogeneous linear systems of differential equations, which is always kind of interesting. So non-homogeneous. That just means that we don't get 0, 0 as our solution, right? Non-homogeneous. Homogeneous means the trivial solution. 0, 0 is the only solution. Non-homogeneous means we don't have that. Non-homogeneous linear systems of differential equations. So let's look at an example. So we have the following system. dx1 dt is equal to -x1 plus 4, and dx2 dt is equal to x1 plus 2x2. So we're going to write this as a matrix equation because it's good to see how to do that. So as a matrix equation, we have that the derivative of the vector x, and that's just both derivatives in one vector, is equal to the matrix -1, 0, 1, 2 times the vector x1, x2. That's going to give us our -x1 and our x1 plus 2x2, but then we still have to add on a 4 in that first component there. So we're going to add on essentially the non-homogeneous part for 0 right there. A way of writing this, like if you're thinking more generally, you can think of this as your dx dt is equal to the matrix A times the vector x plus some other non-zero b vector over there. All right. So our first job is to find the equilibrium. Sometimes it's easier than others, but essentially you're still just doing the usual thing, which is setting each of those equations equal to 0. It's just that in the past, the answer has always been 0, 0. Here it's pretty easy to solve still. So we're going to set -x1 plus 4 equal to 0. Well, that seems like it's obvious that x1 is going to be 4. And then we're going to set x1 plus 2x2 equal to 0. And since we know that x1 is 4, then 2x2 has to be -4, so x2 is going to be -2. So that's our new solution. Or sorry, our new equilibrium. So I would say that our equilibrium x hat is equal to 4, -2. And for whatever reason, we use the hat notation to like represent our equilibrium. That's typical notation from 17D that we're carrying over here. Okay, so the work we're about to do is work that you usually can just kind of skip. But we need to show it at least once or twice to make sure that we understand what we're doing. So what we're going to do now is we're going to make a substitution. I really kind of want to use a new page because I don't want to write all this on this page here. So we're going to make a substitution. Make substitution. I can spell words. Where y1 is equal to x1 minus your x1 equilibrium value, and y2 is equal to x2 minus your x2 equilibrium value. So in this case, we're going to say that y1 is equal to x1 minus 4, and y2 is equal to x2 plus 2. Then we're going to solve for x1 and x2. So easily here, x1 is going to be y1 plus 4, x2 is going to be y2 minus 2. And I'm trying to remind myself why we do this. Yeah, okay, that's fine. All right. Yes, okay. I get it. Cool. So here's what we're going to do now. We're going to take the derivative of y1 and y2. So now, um, we're going to say the derivative of y1 with respect to t. Well, y1 is equal to x1 minus 4. So if we differentiate that, we're going to get the derivative of x1 minus the derivative of 4, which is 0. But we know what dx1 dt is equal to. dx1 dt, from our original system here, dx1 dt is equal to negative x1 plus 4. But then we're going to plug in what x1 is equal to. x1 is equal to y1 plus 4. So check it out. We get negative y1 plus 4 plus 4. We end up getting negative y1 because the 4's cancel. Let's look at the second equation. So dy2 dt, same deal. We're going to say, great, y2 is equal to x2 plus 2. So the derivative of y2 is going to be the derivative of x2 plus 0. Again, the reason we're doing this, by the way, like I was what are we doing? We're doing this so we can figure out what's going on, right? The only way I can take the derivative of y2 is by thinking about what y2 is in terms of x, right? I don't know what the derivative of y2 is, but I know what the derivative of x2 is. The reason we're doing the bigger picture is the reason we're doing this is so we can write our set of differential equations in terms of y instead of in terms of x. Because when we do it in terms of y, we're going to get a homogeneous system which we know how to deal with. That's the whole point. So dx2 dt is equal to x1 plus 2x2. x1 is equal to y1 plus 4. x2 is equal to y2 minus 2. So I get 2 times y2 minus 2. And look what happens. The constant terms are again going to add up to 0. I'm going to get y1 plus 4 plus 2y2 minus 2. Sorry, plus 2y2 minus 4. So I end up getting y1 plus 2y2. And that looks like it's kind of hard to see. Sorry about that. Slightly better. Okay. Here's what I want you to observe. So the only difference between this system of equations here and the one I started off with is that the one I started off with had a constant of 4 there, and this system doesn't have that. But everything else is essentially the same. All the coefficients of the y1s and y2s are the matching coefficients of the x1s and x2s. So when I say we can skip all this work, what I really mean is we could have just said, hey, as long as I know what substitution I'm making, y1 equal to x1 minus its equilibrium value, and y2 equal to x2 minus its equilibrium value, then I can then say, great, my new system is just the same as my old one, use y's instead of x's, and drop any of the constant terms, which is exactly what we're going to write down right now. This whole system here, which I'm going to write down a little bit more compactly, dy1 equal to negative y1, and sorry, dy1 dt, and dy2 dt equal to y1 plus 2y2, we can totally just write as the system, the derivative of the vector y, dt, equal to the matrix, negative 1, 0, 1, 2, multiplied by y1, y2. Very, very similar to what we started with. Just we don't have the parts that's making it not homogeneous anymore. So this here, we're happy about this. This is our homogeneous linear system, which we know how to solve. We've been solving these for days, for weeks, right? How do you solve this? You find the eigenvalues, you find the eigenvectors, you write the solution, blah, 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 blah. Yeah, let's do that. That we're doing next. Yes, it is. So this example was kind of cherry picked because the eigenvalues are really easy to find. You should all be able to look at that matrix and tell me the eigenvalues without batting an eye. For this matrix here, my eigenvalues are positive 2 and negative 1. Actually, I'm gonna change the names I give. I'm gonna say that lambda 2 is 2 and lambda 1 is negative 1. Just because it's confusing when the 2 doesn't go with the 2 and the 1 doesn't go with the 1. Usually I'd label them the other way, but fine. Okay, let's find the eigenvectors. So eigenvectors for lambda 1 equal to negative 1. We have our matrix negative 1, 0, 1, 2 times the vector we're trying to find, x1, x2 equal to, I guess it's technically y1, y2, but whatever, equal to negative 1 times x1, x2. I'll remind you that when we have the situation where the eigenvalues are easy to find like this, it almost always means you have kind of special eigenvectors in that if you look at this first equation here, it doesn't help you. Oh, question. So really, it doesn't matter what we call it. I could have called it A, B. We're just trying to find the eigenvector. This x1 and x2 isn't really specifically representative of the variables we're talking about right now. So it might have been better for me to have used other variables. He likes to use v1 and v2. Let's just use v1 and v2. I'm going to change it to v1 and v2. Those x's look close enough to v's with my penmanship. So I'll point out that the first equation here is negative 1 times v1 equals negative 1 times v1, which is certainly true and also not helpful. It doesn't tell you anything at all. So we have to look at the second equation where we have 1 times v1 plus 2 times v2 equal to negative v2. And that equation is helpful. If we subtract 2v2 from both sides, we get v1 equal to negative 3v2. So let's say we can write our eigenvector as, let's see, v1 should equal negative 3 and v2 should equal positive 1. This one actually isn't too terrible. It's the other one that's actually, I think, a little bit harder to sometimes wrap your brain around. So for the other one, for lambda 2 equal to 2, we have, again, the matrix negative 1, 0, 1, 2 times the eigenvector we're trying to find. Let's call it v1, v2 again, equal to 2 times v1, v2. Now check out the first equation here. You get negative v1 equal to 2 times v1, which means v1 has to equal gotta be 0. We've got no other choice, right? If a multiple of something equals a different multiple of something, the only thing that something can be is 0. So we get v1 equal to 0, and that's enough. If you know that one of the components is 0, you know the other component has to be not 0. But literally, you can pick any other number, but we always pick 1 because we're boring. So our vector here is going to be v2 equal to 0, 1. Right, so one component is 0, the other component is whatever you want it to be. Which means your eigenvector points straight up. 0, 1, 0, 3, 0, 7, all would be valid choices. 0, negative 3 would also be a valid choice, right? Just doesn't matter if it points straight up or straight down, as long as it's in the same or opposite direction. Let's write our solution now. So here's our general solution for y, right? We're still talking about y's right now, even though I accidentally used that for a moment. So the solution to this system, right, dy dt equals negative 1, 0, 1, 2 times y1, y2. Our solution is going to be the very general solution that y1, y2 is equal to c1 e to the lambda 1 t times v1 plus c2 e to the lambda 2 t times v2. Which in this case is going to be, let's see what we've got here. C1 e to the lambda 1 is negative 1t times v1, which is negative 3, 1, plus c2 e to the lambda 2t, so e to the 2t times v2, which was 0, 1. And that's our general solution. That's what our y1, y2 is equal to. which you might just call y of t. But we were trying to find the solution for x. So we need to go back and say, well, all right, it's not hard. That's not the words. It's not that hard to do. We know that y1 is equal to x1 minus 4. And y2 is equal to x2 plus 2. So what we can do here is we can just kind of take this vector and add on the 4, negative 2 to the other side and say that, great, x1, x2 is equal to c1 e to the negative t times the vector negative 3, 1 plus c2 e to the 2t times the vector 0, 1 plus the vector 4, negative 2. Oh, look. He says before knowing exactly what he's going to say. Oh, look. We're just adding on the equilibrium. So, long story short, you can take, okay, I'm writing this right. You can take your original system, find the equilibrium, and then not do any of the garbage we just did. It's not garbage, it was useful. Not do any of the work we just did. Instead, say, cool, I'm just going to ignore the constants in my system here. Treat my matrix A like it's negative 1, 0, 1, 2, right? Just using the coefficients you've got for the variables you've got. Solve that system, and then at the end of that solution, tack on the equilibrium. And that always works. It's not like a trick for this one example. It's going to work every time. Yeah. I will say one more thing here. If we were going to write out like each piece, because sometimes people like to separate the pieces. I don't really like to, but if we wanted to, we can say that x1 of t is equal to negative 3 c1 e to the negative t plus 0 plus 4, and x2 of t is equal to c1 e to the negative t plus c2 e to the negative t, c2 e to the 2t, apologies, minus 2. Yeah. I mean, if there were initial conditions, we could solve for them and find C1 and C2. Questions about any of this? It's not too terrible. I do like showing the work, but yeah. So let's do one more example. And I think we'll do this next example by not showing the work first. And then we'll go back and reconstitute the work to kind of verify to ourselves that we didn't need to actually do it. Okay. So, see if I can make myself believe it. So I will admit fully, this is one of the topics that I used to struggle with a bit. Maybe still do a little bit because it just feels like a little weird. Let's look at this next example. We're going to solve dx. He never strays from x1 and x2, right? It's always x1 and x2. It's never x and y. Okay. Almost always x1, x2. Okay, let's just stick with x1, x2. Not my favorite, but you know what? You don't always get what you want. So dx1 dt is going to equal negative 2x1 plus x2 plus, is that a 4? It is. And the x2 dt is going to equal x1 minus 2x2 plus 1. And we will have initial conditions as well. Our initial conditions are going to be kind of basic. x1 of 0 equals 0, x2 of 0 equals 0. Kind of the least interesting initial conditions, but hey, it's fine. Yeah, we're going to start by finding the equilibrium. So equilibrium is going to be a little harder to find this time. We're still just going to set each of these equations equal to 0. So you have negative 2x1 plus x2 plus 4 equals 0, and x1 minus 2x2 plus 1 equals 0. You could either isolate a variable in one equation and plug it into the other one, or you could use elimination and multiply one of these equations by a constant so that you can add them together and then something will be eliminated. I tend to prefer elimination. So really you could pick either one. You could either multiply the first equation by 2 and add them together, cancel out the x2s, or we can multiply the second equation by 2 and add them together to cancel out the x1s. Either way will work. Let's do the second equation. So I multiply this whole equation by 2. Now I'm going to have 2x1 minus 4x2 plus 2 equal to 0. If I add this equation and that equation, I'm going to get no x1. x2 plus negative 4x2 is negative 3x2. And 4 plus 2 is 6. Looks like we're going to get x2 equal to 2. There is one downside to the elimination method, which is then you still have that you don't have one of the variables solved for, so you still have to go back and plug into one of the equations and then actually do a little bit of work still. So plugging that into either equation, let's plug it into the first equation here. Negative 2x1 plus 2 plus 4 equals 0. So it looks like 6 is equal to 2x1. So x1 is equal to 3. So my equilibrium, my x hat as a vector is going to equal 3, 2. So at the end of the whole process, after I found my solution, I'm going to add on the vector 3, 2. That's kind of it. That's all we're going to use that for, really. So now let's look at our matrix. Our A matrix, we're just looking at the coefficients of the variables. It's going to be negative 2, 1, 1, negative 2. Anything ridiculous here? Nope, totally not ridiculous. Great. Eigenvalues, eigenvectors. I do a little more work here. So this one actually has an interesting a thing to observe, I think. So to find the eigenvalues, the determinant of A minus lambda I, that's going to be negative 2 minus lambda times negative 2 minus lambda minus 1 times 1 equal to 0. Let's give ourselves some room here. Normally, I'd multiply this out and solve. But if these are the same, it's easier to do the following thing. Just say we have negative 2 minus lambda squared, and bring that minus 1 over to the other side as a positive 1. Equals positive 1. And then you can square root both sides and say, whether it's a positive or a negative, right? If it's negative, you can square root both sides and get imaginary results. But here we're going to get that negative 2 minus lambda is equal to plus or minus the square root of 1, which is 1. And then we can solve for lambda and say negative lambda equals 2 plus or minus 1. So lambda is equal to negative 2 minus plus 1, which is still the same as plus or minus 1. So we get negative 2 plus 1, which is negative 1, negative 2 minus 1, which is negative 3. Great. That means we also know that we're going to get stable node for our equilibrium, but that doesn't really matter at this point. Let's find the eigenvectors. So for lambda 1 equal to negative 1, we have negative 2, 1, 1, negative 2 times our vector v1, v2 equal to negative 1 times v1, v2. So we're going to get negative 2 v1 plus v2 equal to negative v1. Adding 2v1 to both sides, you get v2 equal to v1. So our eigenvector here is going to be 1, 1. And then let's carve out something over here. For lambda 2 equal to negative 3. Same deal. Negative 2, 1, 1, negative 2 times v1, v2 equals negative 3 times v1, v2. So now our first equation is negative 2 times v1 plus v2 equals negative 3 times v1. But add 2v1 here, I get v2 equal to negative v1. So my eigenvector is going to be, I would pick v1 equal to 1, v2 equal to negative 1. So there's my eigenvector. Oops, you can't quite see that. Sorry about that. Now let's write our general solution. So our general solution And even though I didn't do the whole u substitution with y things, or sorry, the y substitution with y, I'm still going to write it in terms of y just for the moment. So the y solution would be y as a vector equal to y1, y2 is just going to equal c1e to the lambda 1t times v1 plus c2e to the lambda 2t times v2. That's going to be c1e to the negative t times 1 plus c2e to the negative 3t times 1 negative 1. We shouldn't find our constants yet, though, because they're in terms of x, not in terms of y. So then our x solution is going to exactly be just take that solution we found and add on our equilibrium, which was 3, 2. It's going to be c1 e to the negative t times 1, 1 plus c2 e to the negative 3t times 1, negative 1 plus 3, 2. And now we can find our initial conditions, our C1 and C2 using our initial conditions. So we know that x1 of 0 is 0, x2 of 0 is 0. So plugging those in, we get 0, 0 equal to, okay, let's be careful here. When you plug in 0 for t, which is almost always what you're plugging in, the e to the whatever just becomes 1. So we get C1 times 1, 1 plus C2 times 1, negative 1 plus 3, 2. How much work do we want to do? Good question. Well, I don't know. It really depends on how much, like, I like doing this by writing a matrix equation, but I feel like it's more work than we really want to do. So here's what I'd probably do. I would just write it out as C1 plus C2 plus 3 equals 0. C1 minus C2 plus 2 equals 0. That seems pretty easy to add those two equations together to eliminate the C2s and get 2c1 plus 5 equals 0. So c1 equals negative 5 halves. And then plug that into either one of these to get that c2 is going to equal, I think, negative 1 half. I think, yeah, negative 1 half. Right? So if you do negative 5 halves minus c2 plus 2 equals 0, you get that negative 1 half on the left equals positive c2 on the right. Cool. So then our final specific particular solution is that x1 of t, x2 of t is equal to negative 5 halves e to the negative t times 1, 1 minus 1 half e to the negative 3t 1, negative 1 plus 3, 2. Whew. All right, so I did say we were going to show that we could do the other work that we're missing in the middle. The work that's missing in the middle isn't that terrible. I think we have enough time to do it. So let's actually go back for a second. So the work that we didn't do that would have led to the same result would have been to have said, okay, we're going to reminding ourselves that our equilibrium was 3, 2. We're going to let y1 equal x1 minus 3, y2 equal x2 minus 2. The reason you're doing this, by the way, is essentially you're saying, okay, great. If 3, 2 is the equilibrium for x's, then 0, 0 is going to be the equilibrium for y's. Right? If x1 is 3 and x2 is 0, y1 is 0 and y2 is 0. That's why we make this choice. And then we also solve these for y. So we get, or sorry, for x, we get x1 equal to y1 plus 3. We get x2 equal to y2 plus 2. Then we do the usual thing where we say, okay, great. Our dy1 dt is really equal to, well, the derivative of y1 is just going to be the derivative of x1 minus 0. Similarly, the derivative of y2 is going to be the derivative of x2 minus 0. Y1 and x1 and y2 and x2 always have the same derivatives, right? When you say something is equal to something else plus or minus a constant, you're still getting the same thing. It's kind of like how we did Newton's law of cooling way back when, where we said instead of saying like the rate of change of this thing is proportional to the population size, we said like the rate of change of this thing is proportional to the difference in this thing and this other thing, which is almost the same thing. I know I'm kind of alluding to something that was a while ago, but it's the same idea. And then dx1 dt, well, we know that dx1 dt from way back in the beginning of our situation here, looking back at our original differential equations here, we had that dx1 dt was equal to negative 2x1. I have to make sure I'm not doing something. So this is where I have to make sure I don't get too weird about this. Yeah, no, that's right. Okay, yeah, just yeah. It's going to be negative 2x1 off my spot here, sorry, plus x2 plus 4. dx2 dt is going to be x1 minus 2x2 plus 1. Those are just the original differential equations we started this process with. And then we're going to plug in what x1 and x2 are equal to. Look what happens. We get negative 2 times y1 plus 3 plus x2, which is y2 plus 2 plus 4. And look what happens. The constants cancel out. You get negative 6 plus 2 plus 4. That's 0. And the y things have exactly the right coefficients. Negative 2 times y1 plus y2. Same deal down here. You're going to get y1 plus 3 minus 2 times y2 plus 2 plus 1. When you add it all together, you're going to get y1 minus 2y2, and the 3 minus 4 plus 1 adds up to 0. So your new system is that dy1 dt, dy2 dt is equal to the matrix negative 2, 1, 1, negative 2 times y1, y2, which is exactly the matrix we started working with. So then everything else then kind of falls out. This leads to the eigenvalues and eigenvectors that we got. And then you could either show that our solution, right? You can go back and say that means that we're going to have that. I know we're out of time. Give me one sec. We have the y1, y2 is equal to c1 e to the lambda 1. Sorry, lambda 1 is negative 1. Negative 1 times t. Sorry, that looks gross. Times v1, which is 1, 1, plus c2 e to the lambda 2, which is negative 3t times 1, negative 1. And then to figure out what x1 and x2 are, you just plug in x1 minus 3 for y1 and x2 minus 2 for y2, which results in adding the 3, 2 to the other side. So I'll say it one last time. You don't have to do all this work that we're just showing right here, right? You can just find the equilibrium, set it aside, solve the coefficient matrix with the eigenvalues and eigenvectors in the usual way, get the solution in the usual way. Then after you got the solution, add back on the equilibrium. And then if you have to find constants, you can find constants using the initial conditions. And I don't think we do this stuff if your eigenvalues are complex. It could be extra terrible. All right, that's all for today. You all on Monday. And you don't have it. So your exam is scheduled for a week from the coming Monday, right? It's for March 3rd, which is the first Monday in March. I'll work on writing up a practice exam.